Hello, everyone. Thank you for coming to our April online lecture event. We are the Center for Climate Science and Engineering at the University of Toronto. We host monthly guest lectures. My name is Mohammed Jalayer. I am the CSE manager. Today, we are pleased to feature Dr. Ahmed Ibrahim from the University of Toronto. Before we get there, I'd like to go through the land acknowledgements. We wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still home to many indigenous people from across the Turtle Island, and we are grateful to have the opportunity to work on this land. For those who haven't attended our guest lecture events before, the CSE is a research and education center within the Civil and Mineral Engineering Department at the University of Toronto, and it was established in 2019. The CSE consists of a diverse and multidisciplinary team of faculty members who collaborate on interdisciplinary research at the intersection of climate science and engineering. Our center's director is Oya Marjan, and she focuses on structural analysis. Daniel Paulson focuses on life cycle assessment. Ahmed Ibrahim works on hydrologic variability and processes. He's going to give a presentation today. Karen Smith focuses on atmospheric science. Mohammed Bashir focuses on hydrologic and water resource systems. Paul Kushner looks at climate dynamics. Sam Markov from the University of California, Merced, focuses on sustainability and resilience. And then me, the CSE manager. So one of the primary initiatives undertaken by the CSE focuses on providing education in climate science and engineering. We have developed and launched 2 graduate level courses at the University of Toronto. Additionally, we have created 8 online learning modules that are now accessible for use across higher education institutions in Ontario. We also design and run 2 courses through the University of Toronto's Deep Summer Academy for high school students. Furthermore, our faculty members are engaged in collaborative research projects at the intersection of climate science and engineering. Also, our team organizes outreach activities just like this one, where we invite the public or university community to give a presentation on topics that are aligned with the mandate and vision we have at the center. Now, I'd like to introduce today's guest lecture speaker. Ahmed Ibrahim is an assistant professor in the Department of Civil and Mineral Engineering and School of the Environment at the University of Toronto. He received his PhD in the Department of Civil and Environmental Engineering at the Massachusetts Institute of Technology and completed his postdoctoral work in the Department of Atmospheric Sciences at the University of Illinois Urbana-Champaign. His main research interests are in hydrological processes and mechanism of the hydrologic variability, with the aim of developing adaptive strategies for managing regional water resources in a changing global climate. He is going to give a presentation on adapting the riverine flooding in a changing global climate. Dr. Ibrahim, welcome. We are very excited to learn more about your presentation. I am passing it over to you now. The floor is yours.
Thank you so much, Mohammed. I'll share my screen and hopefully everyone can see it.
Yeah, we can see it. Great.
Can you all see my screen?
Yes.
Super. Well, thank you all for inviting me to come talk to you today about my work, and thank you again, Mohammed, for putting all of this together. It's been wonderful joining the department and getting to know everyone. So today I'm going to talk about flooding, and as a first step, I want to sort of acknowledge some of the people that were instrumental in this work at my previous department at Illinois. It's recently been renamed the Environmental Science Division of Argonne National Laboratory and the Discovery Partners Institute of the Illinois State Government. So the work that I will describe today is what I show here in blue, and if you're interested, you can read more about this work in that paper. So I want to first distinguish between the types of floods that are out there so that we are clear as to what this talk is about, and to sort of appreciate some of the processes that are involved in different types of flooding. So in the figure to the left, the one that I'm showing here, this is a figure of Venice. This is Venice in in Italy. And as you can see, there's water on the ground. So this is an example of what we would call coastal flooding. The processes involved in that are quite different. For example, sea level rise, sort of tides can, cause some of this. You can also have sort of land subsidence, which is actually the particular major cause of this phenomena in Venice. So that is not what we're going to be talking about today. Today, we will focus on what I call riverine flooding, which is the figure to the right. That figure was taken after a flooding event in the city of St. Louis in Missouri. So riverine flooding essentially just means that the river is unable to carry all the water in it that comes in it. So therefore, the water spills to the land area around it and sort of submerges everything around. So today we will focus on this type of flooding. And in this particular region, we would analyze some of the causes of this type of flooding. So the place where we would focus is the Missouri River Basin. This is the figure that I'm showing here. It's a very important basin for the U.S. economy. And I've highlighted the reasons here. It's basically, 46% of wheat grown in the U.S. comes from this basin, 22% of corn, and a lot of cattle. And most of this is irrigation fed. Basically, it depends on rainfall. Just to orient us, so this is this MT, here's the state of Montana. If you go north a bit, you get to Alberta. Okay, so we are sort of up here somewhere. So this is up here is Canada, and north here is like Alberta. You can see that in the basin there's a very clear distribution of elevation. So this is the Rockies, right? So you see it extends on the western side of the basin all the way, towards Alberta. This is important for so many reasons, and I'll discuss some of this later. So the U.S. Army Corps manages a system of reservoirs in this basin to achieve a diverse set of goals. So the first, obviously, is to provide water for irrigation. The second is to prevent flooding, especially in the lower reaches of the basin. Okay, so anywhere between, say, for example, half of Wyoming. Wyoming is WY. So from there southward tends to get a lot of flooding. So these reservoirs, which I've indicated here as R1, Reservoir 1, Reservoir 2, Reservoir 3, as well as until Reservoir 6, they were designed to meet a series of goals. One, provide water for irrigation. Another is to provide electricity. So these are simultaneously hydropower plants. And then a third reason is to, as I mentioned, prevent flooding downstream. So it's a multi-use system of reservoirs, and it's been very difficult to achieve these goals because in addition to this sort of, economic uses, there are also sort of legislative mandates in terms of who gets how much water, how much space has to be left behind, to collect more rainfall. So basically what the U.S. Army Corps has to do is to try to balance this out. In any given year, they have to keep enough water to satisfy irrigation upstream. They have to also hold enough water so that, when it's raining a lot downstream, the release from these reservoirs do not flood the people downstream. At the same time, this same water has to generate sufficient amount of electricity that is powering significant, sort of industrial activity in the region. So it's a very difficult task because nobody knows how much rain is coming in the bottom. If you release too much rain and then too much water from the reservoirs and there isn't enough rain upstream, then there's no water for irrigation. So they never quite get it right. And in 2011, there was a serious flooding event that basically destroyed billions of dollars worth of property and human life, like as well as human life in the south of the basin. So it was after that event that the Army Corps, so usually after any one of these events, there's a sort of summary, like analysis of events. So in that analysis, they stated that it's a big challenge, that they can't predict rainfall, the variability of rainfall. And therefore, it is very difficult to know how much water to keep and when to release the water. There is another difficult challenge. You see, in the states of North Dakota and South Dakota, where the main stem of the river goes through, the section of the river there tends to freeze up during the winter. So if you release a lot of water from upstream, that water essentially turns into ice. It basically forms like an ice dam, in those states. And if the temperature in that section suddenly increases, like as spring comes along, that ice dam can burst and release tremendous amount of water. So this is another challenge in sort of getting, the release right. So the word here is the reservoir release. So all of these things have to be sort of integrated together to achieve the balance here. So the problem, as I mentioned here, is sort of adapting these rules, and then it's further complicated by global climate change and sort of changes in regional hydrologic variability, and there's more rain, less rain. So they basically highlighted that it's difficult. We can't figure it out. We need to find better approaches. Obviously, one thing you can do is just build more reservoirs, right? And just say, okay, we'll build more reservoirs and hold more water, and that way we don't flood anyone. But it's hard to do that. There isn't as much land as there used to be before. There's no appetite for huge constructions, and things are complicated that way. Another thing you can do is to take the water and put it in the Ogallala aquifer. So a lot of this, the region underneath this basin is what we would call the Ogallala aquifer. It's been water from there has been pumped for many, many decades. So there's a lot of space, but the aquifer itself is shrinking because you've removed a lot of water. So there's a lot of complexity. So that can't be done. So one way that when this problem came to me that I thought about was, okay, you already have these reservoirs there. You already have the operating rules for releasing the water. Suppose we can look into the structure of variability, look at the things that control water in this basin, and find new opportunities to exploit, sort of the infrastructure without building anything new. So I'm not following the chat, so maybe I'll take questions afterwards. But if there's anything that needs clarification, please, just speak up so I can clarify. So my suggestion was, okay, maybe we don't need to build anything. Maybe we just need to sort of, find, clever ways to look at how the hydrologic system overlying this basin or the basin itself is operating, and then look at how we can align these objectives in another careful way so that we get optimal results. We don't flood people. We have enough water. There's electricity, and we just sort of very low cost solution. So that was the intention of taking on this work. So just to give you a good feel of how this natural system works, I've written down here sort of a basic, simple mass balance equation, which I say P for precipitation is approximately equal to evapotranspiration plus rainfall. Okay, so that comes from the fact that rainfall must be divided into 3 parts. So the first one is the one that goes inside the ground. You call that infiltration. So that, in general, is order of magnitude smaller. It's very small because the rate of water going into the ground is typically very slow. So here we're going to neglect that because it's not a major impact. The second part is one that goes back up, which is the evapotranspiration. That's what I've called ET here. And then the third part is runoff, which is the one that we call rivers, that goes into the rivers. That's what all of this system of reservoirs, that's what it depends on. But this basin is further complicated by something else, which is air temperature. Air temperature comes in because sometimes the rain doesn't reach the ground as liquid water. It reaches the ground as solid water, which is snow. So air temperature controls whether or not it's snow or liquid. And it also controls when that water is released in terms of liquid. That is the thawing of snow. So what air temperature does is that it introduces a lag into how water moves. It basically retains the water in the basin as it helps to retain the water as storage. And then it messes around with, the timing of events. So, and the upper half of the basin gets all of its precipitation in snow. So all that snow accumulates, and then as temperature changes, that snow starts to melt and turns into liquid. So this again adds, complexity. So basically what's happening here is that the release rate, the reservoir release rates, depends on three significant factors. The first is how much rain actually comes in. That's the water source. And then the sink, which is evapotranspiration. And then the thing that introduces like delay, like lag into the process, which is air temperature. So if you want to understand the nature of variability in this basin, you have to really get down to understanding how these three things adjust during the annual cycle, which is the element that we're interested in. The annual cycle is the basis for this, reservoir release for managing this system. And that's what we want to get at. We want to know how P, ET, and T air sort of behave during the annual cycle. So that's what we're going to try and look at in the rest of the talk and see what it means for managing this system. So as a first step, an important thing to sort of point out is that because the atmosphere actually cannot hold a lot of water, when it rains, we have to ask, how did the water get there? So in the United States, we have to ask, how is the water arriving over the basin? Well, the water arrives there because wind brings it. Wind is the vehicle. So we want to first look at the distribution of wind over the basin. And the United States is a bit unique in the sense that, its topography is such that, as I mentioned in the last figure, in the western side, here that you saw before, is very mountainous. If you go even further west, there's still a lot of mountains. And then go further west is the Pacific Ocean. In the south, you have a lot of deserts and then the Atlantic Ocean. In the east is also the Atlantic. In the north, where we are, is just land. So these three things, or four things, if you like, contribute significantly to the structure of wind during the annual cycle. So basically, there are four kinds of winds. The one is the one coming from the north, where we are. It's cold and dry. I actually discovered that even more familiarly when I arrived here in Canada. It's very cold and dry. Okay, it's coming down from the north, like polar wind, we call it. It's the polar wind. The one coming from the west is mainly the Pacific wind. It's moist, okay, because it's coming from the ocean, and then it's warm. Okay, it's not as cold as the one coming from the north. But that wind, as it approaches land, it has to go over the mountains, right? So it has to go over the mountains in the west, come down, and then go over another set of mountains, that you saw in the previous map. So all of this going up and down sort of modifies how much water is in the wind, how cold it is, and all of that stuff. Okay, so, and then from the south, you also have another system, which is the Atlantic. That water, that air, on the other hand, is also moist. Okay, it's moist because it's coming from the ocean, and it's also warm. So as you can see in this figure, all of the wind, the strong winds tend to originate, from the ocean. So when we analyze the wind structure, we find that you can essentially separate the annual cycle into two seasons. The one is one that is dominated by the north wind. North wind here meaning that, the wind is coming from the northern direction. Okay, so basically what happens is the cold wind from the north comes down, and then the western wind that has like moisture, they collide over the United States. And when that happens, you can have snow and all kinds of other like effects. So basically in the from October to March, you have the control of wind is the north wind, which is cold. So you have a lot of snow. Okay, so that's what I'm showing here. So I'm showing you here sort of the distribution. You can see that around here in the south, as the wind is approaching the US, it sort of bifurcates, it splits into two because of the mountains. And then the figure I'm going to show you next, you'll see how that wind behaves. You can see here, right above Colorado here, when the wind bifurcates, it goes right above the mountain or turns around it and then starts to come over down. And you can see I'm showing here the basin in red lines here, how the wind sort of accelerates when it gets over the basin. So this is what the sort of north wind does in the snow season. And the second season, which is what I call here the rain season, it's the south wind. So a lot of this sort of moisture now is coming from the Atlantic Ocean. So this is the season of the hurricanes. You may have heard of like a lot of hurricanes in the US. This is basically it. So when you see that, you have those hurricanes, they come from the Atlantic, they go in through the Gulf of Mexico, which is right here in the bottom. So it is that wind that is supplying moisture into land. Now, during this season, however, it is warm here. So there's no cold wind to freeze it, to sort of create snow. So it's a lot of liquid water. So this is basically the two distribution of wind. So please keep this in mind as you will see that this has a huge impact on sort of the variability of P and ET as well as TL. So now, the systems that I just described earlier, the Pacific, the Atlantic, the polar wind coming from here, these are very complex, huge systems, globally. There's no way to observe what's happening. The only way we can get information about them is to look at the global climate models. These are the only tools that can simulate the dynamics of these systems in a continuous way, together in one unit. So to evaluate variability, whether in this decade or in the future decade, we have to go look into these models to see what they're doing. So what we did was to look at a set of models that were shown to be reliable over the US, and that's what I'm showing in the figure here. The paper is what I indicated up here. So what we want to do is to sort of ask, okay, our hypothesis for this work was, under the expected variability of in terms of global climate change, that the months that dominate variability in these three variables are going to stay unchanged, right? That kind of makes sense if you think about it. Everybody knows that we see winter, spring, summer, and fall every year. They all come whether or not we like it, but sort of the magnitude, how cold it gets or how warm it is tends to be a bit different. So our hypothesis to let's say, let's look into these models and see what they're doing and be able to examine, on the one hand, the nature of variability in this variables, and then on the other hand, how that variability is going to change into the future. Okay, so we looked into this model. So these models individually themselves, they're not very reliable, but one technique is to sort of take an ensemble. So in this table here, there's, I think, 1, 2, 3, 4, 5, 7, 8 of them. So what you're going to look at, the results we're going to look at is just an ensemble. So you take the same variable from the models that have been downscaled, and then you just average them. So that is considered more reliable, in terms of looking at global model results. So the first step, obviously, is to compare it to what's happening in the basin, right? Like what's happening, what is the actually observed, variables in the basin. Now, we have luck because the US, you might think of it as just a really dense network of observational data. So there's a lot of observational data. So in that sense, you can think of the entire US, all the airports, they have, sort of weather stations, counties, they're everywhere. So it's basically like an instrumented, like hydrologic experimental basin. If you just think of it as a land surrounded by ocean, except in the north. So we took this data, and then the data is compiled first from everywhere in the US and then interpolated to sort of cover places where there aren't observational data. So we then compare it with the ensemble, and it's reasonable. So we know that like what the models are simulating is actually consistent with what is happening in the basin. So we can then say, okay, let's see what the models say for the future. Obviously, there are differences. As you can see, there's sometimes a bit of a lag in the months of winter are a bit different, but overall we're pretty satisfied that it captures the seasonal cycle, which is the key element, the annual cycle. Now, as I mentioned before, everyone knows that like we have our seasons as they come, but they're typically not exact. Some winters are colder, some summers are warmer. And the reason for this is that, the hydrologic cycle itself sort of depends on insolation. That's how much sunlight is coming in. That's where the heat source, the energy source. It also depends on, the distribution of pressure in the atmosphere, which drives the wind. It also depends on the ocean evaporation, where all the water comes from. So because of all of these other sort of, complexities, it's not as though, we would expect exact, rigid, sort of seasonal cycle, as though that like the distance between two planets. That's not, what it is. The drivers are similar, but when it manifests around us, there are slight changes. So because of that, a very convenient way to think about interannual variability is that it's just like a cyclical change in the probabilities. The events themselves, they still occur. We get winter, we get summer, but their probabilities, they tend to go up or down. They can be closer to the mean or a bit farther away from the mean. So in that sense, it's just like, just if you just think of it that way, it's just probabilities. You can just, from there, you can run away with it and sort of begin to look at the numbers. But for here, we'll focus on like its physical manifestation. So our metric is what I call here the mean absolute deviation. It's just the average linear distance. Okay, definition is just, so you take for any given decade, there's 10 Januaries, there's 10 Februaries. So you take the average of all that, average of 10 January. So you have the average of January for that decade. So you then subtract each January from that average. It can be more, it can be less, but we don't care. We only want the absolute value, so we want just the distance. Okay, so you subtract, you get all those small numbers, the difference of each January from the decadal mean, and then you sum them and take the average. So that gives you the average linear distance from the multi-year mean. So that's what we mean here. So that's our metric for looking at how far away from the mean of this decade is January when we look into the future. How far away from the mean of this February, the February in this decade compared to the February in future decades. That's what we're asking. Subsequently for March, April, May, June, July until December. So that's what we're going to be looking at. Okay. So let me now show you some of the results. So these are some of the projected results. As you can see here, this is just the annual mean absolute deviation. So what I described before was for each month, but you can do it for each year, right? So you take the decadal mean for each year and you subtract each year from that decadal mean, you take the sum of the absolute value, divide by 10. Okay, it gives you the average linear distance. So that's what you're looking at here. You can see that in the left panel here, the top is mean MAD for precipitation, the bottom is for evapotranspiration, and the middle is evapotranspiration, and the bottom is air temperature. So you can see that the southern part of the basin has a higher mean absolute deviation, meaning that like precipitation there has a huge, bigger spread around its mean compared to the northern section of the basin, right? And you can see that evapotranspiration actually follows, in a certain sense, the south has a stronger mean absolute deviation. This makes sense because you can only evapotranspirate if you have water, right? So and because it is the rain that is bringing the water, so it makes sense that like ET sort of is following what P is doing, right? But for air temperature, on the other hand, you can see how that distribution is completely different from what P and ET is doing. The reasons for this, I'll get to it later in this talk. When we compare what is happening between this decade that we're in to the 3 future decades, you're now looking at that in the figures from here to that I call A2, A3, and A4 for precipitation. You can see that as we move into the future, the South, once again, has a larger mean absolute deviation, meaning that compared to the mean of this decade, there's a larger spread on precipitation. So you can have a lot of rain compared to what you have already gotten used to in the South. This means that you just can't release whatever amount of water you are already releasing this decade. If you do that, and that water gets downstream, and then there is a lot of rain, you're going to bury a lot of people downstream because the river can't carry all of that, as I mentioned before. In the middle row, you can also see that in a certain way, ET is following what P is doing, which makes sense. ET is only doing what it's doing because there's water to evapotranspirate, and the source is P. But when you look at air temperature, it's very different. You can see that around the edges of the basin, as you move into the future, there's a stronger sort of positive deviation, meaning that it gets warmer. There are times as you go into the future where these regions are much warmer than what you're used to now. And then in the South, you have a sort of a slightly lower, smaller spread, meaning that it can be a bit colder than what you're used to now. But for us, I'm showing this just to highlight this sort of annual picture. What we really care about is what's happening every month, because that's the basic schedule for releasing water. So we will now look at what happens first for precipitation. So I'm showing here in the sort of histograms in the top, I'm showing here the MAD for each month in this decade as well as for the future 3 decades. And the bottom sort of plots here, I'm showing you the maps of the basin, how this MAD is distributed along in the basin. And in the figures that I've highlighted, there are columns in black. I'm showing you the months with the highest sort of mean absolute deviation, defined as the 6 months above the median. Okay. So you can see that the months with the highest basically start from April to September. If you recall, these are the months in which the rain season wind dominates. Okay, it makes sense. The reason why you have this variability is because this is the month in which rainfall is largest in the basin. Okay, this is all consistent with what we've seen before. And when we look into the future, these same 6 months, they remain the months with the highest variability. So they don't change, which is telling us that whatever the system governing precipitation, whether it is the water coming from Pacific, whether it is the water coming from the Atlantic, whether it's the cold air from the polar region where we are, however they manifest themselves over this basin, these same 6 months are going to be your problem months. Okay, so you can then isolate, these months and say, okay, we want to, as a reservoir release approach, we want to really look at how we are going to target these months, because now we know that they're not going to change looking into the future. When we go look at evapotranspiration, exactly the same structure is evident. Again, it makes sense. ET follows P. You only evaporate if you have water. So the system, again, is telling us that it is going to stay unchanged as we look into the future. However, when we get to air temperature, something interesting is happening. Only 4 months among the 6 that are dominant in this season retain their probabilities when we go into the future. In 2 decades into the future, 2 of the months have probabilities that are exceeded by probabilities in June, July. What this means is that these months, if you are releasing a certain amount of water during these months now, You can't do that again as you move into the future because it can suddenly get warmer or it can suddenly get colder. Now, warmer here means you can release water that is held in snow, right? And colder here means that, like, in the seasons that you expect water to just flow away, the river can ice up, and then you can start building, sort of an ice dam. So that's basically the interpretation of this exceedance in the probabilities of air temperature as you move into the future. So basically, to summarize this whole thing, I then analyzed sort of how the Army Corps sort of does their reservoir release now. They basically have two seasons. In the 3 winter months, which I'm indicating here as the low water release rates, they reduce the water release because of ice in North Dakota and South Dakota. And then in the rest of the 9 months, they quickly try to release water because legislation, there is a law that says every year there must be that much empty space in the reservoir so that when water comes, it has a place to go. So they have to quickly get rid of all of that water before the next runoff cycle. They do that in 9 months. Because of this analysis, we proposed a 3 sort of a different structure of water reservoir release. From December to March, we say to release, to have a low water release rates. The reason for this is that this is the months in which air temperature is lowest, meaning that you can create ice dams. And this is the months in which the variability of air temperature is highest, meaning that it can get even colder, or you can suddenly have a warm spell that releases all of that water. So therefore, to be on the safe side, you should release the least amount of water you can do. From May to July, this is when precipitation is highest. And this is when its variability is highest, meaning that you have a lot of rain and you can get even more. So we say that you should be a bit conservative, release medium rates. Now, from April, August, and October, precipitation is low. And the variability of precipitation itself is low. So you can imagine that the window around P now is tight, so that you keep that, you just release all the water you need to during this period, because there's less chance that you will flood people downstream. So we say that that this proposed release strategy should now be validated with sort of the observation in the basin, and that this has more chances of reducing flooding. So this type of work is although it's just starting around here, it's highly in operation in Australia, for example, where they use a lot of reservoirs, and their worry is sort of flooding because of La Nina. So one of the biggest flooding events in Australia is essentially because of this reason. They kept too much water, and they didn't anticipate that La Nina was coming. And then when La Nina came, we had so much rain, but they had no space to put the water. So they suddenly had to release all of that water and flooded everybody downstream. So the point is that this type of work can be used to sort of, get more value out of infrastructure rather than, sort of building and building and building. And I hope that, it can be useful to the folks in the Missouri River Basin. So I'll stop there and take any questions that you may have.